In a moment that will echo through the annals of human history, NASA's James Webb Space Telescope, JWST, the most advanced observatory ever constructed, has pulled back the veil on the cosmos to reveal a discovery so profound it challenges the very foundations of our understanding. Launched to peer into the deepest reaches of space, this technological marvel has captured luminous images that transcend mere beauty. They hint at the existence of a separate universe, a reality so alien it defies the laws of physics as we know them. This is not just a glimpse into the distant past or a far-off galaxy. It is a window into a cosmos that operates under entirely different rules, a revelation that could rewrite science, philosophy, and our perception of existence itself. Buckle up, because the universe, or rather universes, has just become infinitely more mysterious, and the journey to understand this discovery is only beginning. Imagine a telescope so powerful it can peer back to the dawn of time, capturing light from the universe's infancy. The JWST, orbiting 1,000,000 miles from Earth, is that instrument, equipped with cutting-edge near-infrared technology designed to unravel the mysteries of cosmic origins. Its mission was ambitious, to fill in the gaps left by predecessors like the Hubble Space Telescope, to map the early universe, and to probe the formation of stars and galaxies. But what it found in a routine scan of a seemingly unremarkable patch of sky was anything but ordinary. The data revealed light signatures bending in ways that defy mathematical consistency, structures too ancient, too massive, and too dense to fit within our cosmological models. This wasn't just another galaxy, it was something far stranger, a pocket of reality that operates independently of our universe, challenging everything we thought we knew about space, time, and existence. The discovery sent shockwaves through the scientific community. Astronomers expecting to refine existing models were instead confronted with evidence of a separate universe, a realm where time flows differently, light scatters in unfamiliar patterns, and gravity warps in ways that defy Einstein's theories. This isn't a distant corner of our own cosmos, but a distinct space-time environment, possibly born from its own Big Bang or an even more exotic cosmic event. The implications are staggering. Our universe, once thought to be the entirety of existence, maybe just one bubble in a vast multiversal sea, each with its own physical laws, timelines, and possibilities. The JWST's images, with their mesmerizing galactic superclusters glowing in aberrant colors, suggest a reality where stars burn without hydrogen fusion, galaxies rotate without dark matter, and the very fabric of existence operates under alien principles. This finding upends the lambda cold dark matter, lambda CDM model, the cornerstone of modern cosmology, which describes a singular, expanding universe driven by dark energy and dark matter. The JWST's data suggests a cosmos that is either self-contained or originates from a different cosmic event, forcing scientists to reconsider the very framework of reality. Theoretical physicists, once relegated to speculative debates about the multiverse, now find themselves with empirical evidence to support their wildest theories. The concept of a multiverse, millions, billions, or even infinite realities, each with unique physical constants, has moved from the fringes of science to the forefront of research. The JWST has not just mapped a new region of space, it has opened a door to a new realm of understanding where the rules of physics are rewritten and the boundaries of possibility are redrawn. The images themselves are nothing short of breathtaking. Vast regions of space glow with colors that don't correspond to any known elements in our universe. Where astronomers expected familiar hydrogen emission lines, they found frequencies that defy explanation. Stars emit radiation inconsistent with Planck's law, and galaxies rotate in ways that suggest an absence of dark matter's influence. These celestial mechanics are guided by principles so foreign they challenge the core tenets of physics. Even more astonishing are the gravitational effects observed around this region. Light from background stars in our universe bends in ways that general relativity cannot fully explain, as if this other universe exerts its own gravitational pull, existing not within our spatial continuum, but overlapping in a higher dimensional space. Picture two soap bubbles touching at their edges, not merging, but sharing a fleeting contact point in a dimension beyond our perception. The JWST may have captured this boundary zone, a cosmic interface where our universe brushes against another, other. This raises profound questions. Could matter, energy, or even information transfer between these realities? Is this interaction stable, or is it a fleeting anomaly? More unsettling is the possibility that our universe is not the primary one, or that the concept of a primary universe is meaningless. If multiple universes exist, they may form an infinite fractal structure, a self-generating multiversal sea where each bubble births others through cosmic events we cannot yet comprehend. The JWST's discovery is not just a new data point, it is a paradigm shift that redefines the cosmos as a layered, interconnected web of realities. The implications of this discovery extend far beyond astronomy. Quantum mechanics, long at odds with general relativity, finds new relevance in this multiversal framework. The idea that particles exist in superposition or that observation collapses wave functions may now apply to entire universes, each representing a different outcome in a vast probability structure. Supercomputers tasked with modeling these implications suggest that universes with different physical constants, where the speed of light varies or the strong nuclear force is weaker, could still support complexity. Even life in forms radically different from our own. Imagine universes where stars never form, but life thrives in cold gas clouds, or where consciousness arises from magnetic fields rather than neural networks. The JWST's data opens a window to these possibilities, challenging us to rethink the nature of existence itself. The cultural and philosophical ramifications are equally profound. For millennia, humanity has asked, are we alone? The search for extraterrestrial life has focused on planets and galaxies within our universe. But the JWST's discovery shifts the paradigm. We may not just share this universe with others, but share existence itself with countless realities. This plurality of existence challenges science, philosophy, and theology, forcing us to reconsider what it means to be human. The symmetry and chaos observed in this alternate universe, wild clusters, twisted formations, and erratic energy fields, suggest a reality that followed a different blueprint from the outset. Time and entropy may operate in reverse, or on a non-linear scale, raising the possibility of a mirror universe dominated by antimatter, or a cosmos where time flows backward relative to our own. As the JWST continues to refine its observations, artificial intelligence is analyzing the data for patterns, anomalies, and potential technological signatures. Regular emissions, repeating pulses, and geometric arrangements hint at the possibility of non-natural phenomena, though scientists remain cautious about claiming evidence of alien civilizations. These findings reignite debates about the fine-tuning problem, why our universe seems perfectly suited for life. If multiple universes exist, each with different physical constants, our existence may be an inevitability rather than a miracle, a product of a cosmic lottery where every combination of physics plays out somewhere. The JWST's discovery also suggests that our universe may not be unique in hosting such junctions, raising the possibility of countless rifts or gateways scattered across space, invisible until instruments like the JWST detect them. The data is overwhelming, with thousands of terabytes of high-resolution readings flooding research institutions worldwide. This discovery will define the future of astronomy, cosmology, and particle physics, spawning new fields of study and inspiring generations of scientists. Parallels are being drawn to abstract mathematical constructs like brane-world cosmology and string theory, once dismissed as untestable, but now finding fertile ground for exploration. In classrooms and coffee shops, the conversation has shifted. Children wonder if their counterparts exist in another universe. Artists imagine alien skies, and writers craft stories that blur the line between fact and fiction. The JWST has stretched the human imagination, reminding us that the universe, or universes, is far vaster and more mysterious than we ever dared to dream. As scientists delve deeper into the JWST's data, a new field of study is emerging: interuniversal dynamics. The boundary between our universe and this newly discovered realm, dubbed the interversal boundary layer, is not a static veil, but a dynamic interface that pulses and shifts as if the two realities are aware of each other's presence. Fluctuations in radiation patterns suggest an exchange of energy or information, challenging the concept of the cosmic horizon, the limit of causal interaction. If another universe can influence ours, even subtly, phenomena like dark energy or cosmic microwave background asymmetries may need reinterpretation. These could be signatures of ancient contact with other realities, ripples from a multiversal interaction that shaped our universe's infancy. The JWST's instruments have revealed matter structures that defy our understanding of of physics, configurations that suggest alternate particle families or a mirror standard model. These findings hint at quantum entanglement across universes, where particles in our reality are paired with counterparts in another, influencing each other across dimensional boundaries. Such discoveries elevate quantum mechanics to a universal constant, transcending not just distance but reality itself. Mathematicians are developing new frameworks, drawing from category theory and algebraic geometry to model these interactions. These models propose heteromorphic transformations, where data crossing the interversal boundary changes in nature, explaining why the JWST's spectroscopic readings defy known norms. The discovery also raises the possibility of nested universes, pockets of reality embedded within our own, formed during cosmic inflation. These microcosms could serve as natural laboratories, testing alternative physical constants and offering insights into the full parameter space of existence. Dimensional stress points, where the symmetries of two universes grind against each other, may produce quantum turbulence, potentially explaining phenomena like gamma-ray bursts or cosmic ray showers. As the JWST continues to map these stress zones, scientists are reclassifying cosmic anomalies, reprocessing old data from missions like Planck and COBE to uncover hidden signatures of multiversal contact. Speculative biologists are imagining life forms in this alternate universe, shaped by its unique constants. In a realm where gravity or quantum coherence behaves differently, life could manifest as photonic hive minds, superfluidic networks, or sentient magnetic fields. These ideas, while hypothetical, are grounded in the JWST's data, which suggests thermodynamic anomalies consistent with highly ordered systems, potential hallmarks of artificial constructs. Meanwhile, engineers are proposing missions to monitor the interversal boundary, from deep space observatories to theoretical propulsion systems that could probe this cosmic interface. The notion of touching another universe, once pure science fiction, is now an engineering challenge tempered by caution about the risks of destabilizing our reality. The JWST's discovery has sparked a renaissance across disciplines. Philosophers debate the nature of consciousness in a multiversal framework, while theologians find parallels in ancient myths of layered worlds. Neuroscience explores whether dreams or intuition could be echoes of alternate realities, and quantum computing considers the possibility of multiversal computation, leveraging different physical laws to achieve unprecedented results. The public imagination is ablaze, with art, media, and literature reinterpreting what it means to exist in a plural cosmos. This discovery is not just a scientific milestone, it is a cultural shift, redefining humanity as residents of a universe among many. As educational institutions pivot to prepare students for multiversal science, new fields like transdimensional physics and comparative universe theory are emerging. The JWST, silently orbiting at Lagrange Point 2, has become more than a telescope. It is a herald of cosmic revelation, proving that the pursuit of knowledge can yield truths that elevate humanity. Its data continues to surprise, with anomalies in time dilation, unidentified emission lines, and gravitational lensing that hint at particles beyond the standard model. Each finding peels back another layer of the cosmic onion, revealing a multiverse that is just beginning to share its secrets. The JWST's findings have introduced a new layer of complexity to the cosmic puzzle, particularly in the realm of causality. The linear progression of cause and effect, a bedrock of classical physics, appears to falter at the interversal boundary. Energy fluctuations detected by the JWST suggest that events in the alternate universe may not follow our temporal logic, with some appearing to echo backward as if their causes originate in our future. This challenges the very notion of time as a universal constant, suggesting that in a multiversal system, time may be cyclical, fractal, or even bidirectional. Such phenomena open the door to radical new models of reality, where the past and future are not fixed but interwoven across dimensional planes, creating a tapestry of existence that defies our linear perceptions. These observations have practical implications for future technologies. If time-inverted signals from another universe can be detected, scientists propose developing instruments sensitive to these anomalies, potentially using superconducting materials to capture ultrafine quantum fluctuations. Such a device could act as a cosmic early warning system, detecting precursors of events across the interversal boundary. The concept of predictive interference, where one universe's temporal flow influences another, could revolutionize observational astronomy, allowing us to anticipate cosmic phenomena before they manifest in our reality. This speculative leap, grounded in the JWST's data, underscores the telescope's role in pushing the boundaries of what we believe is possible. The hypothesis of nested universes adds another layer of intrigue to the JWST's discovery. Rather than an entirely external cosmos, the alternate reality may be a pocket of space-time embedded within our own, a remnant of bubble nucleation during the early universe's inflationary phase. These microcosms, governed by divergent physical laws, could act as natural laboratories where alternative physics play out. The JWST's detection of such a pocket suggests that our universe may be a sponge-like structure riddled with invisible realms that remain undetected unless they intersect with our observable field. This raises the possibility that countless other micro-universes exist, each a crucible for testing the limits of physical possibility. These nested realities could hold the key to understanding the full parameter space of existence. By studying their properties, scientists may uncover why our universe's constants are so finely tuned for life. The JWST's data hints at thermodynamic anomalies that suggest highly ordered systems, potentially indicative of artificial constructs or exotic life forms. If these pockets are indeed laboratories of physics, they could reveal how different combinations of fundamental forces give rise to complexity. The challenge now is to develop instruments capable of probing these realms without disrupting their delicate balance, a task that will require unprecedented collaboration between physicists, engineers, and mathematicians. The concept of dimensional stress points introduces a dynamic element to the JWST's findings. These zones, where the symmetries of two universes collide, may act like cosmic fault lines, generating quantum turbulence that manifests as high-energy phenomena in our universe. The JWST's high-resolution data suggests that gamma-ray bursts and cosmic ray showers, long attributed to black holes or supernovae, could occasionally result from micro-collapses at these stress points. This new lens offers a way to reclassify cosmic anomalies, providing a framework for understanding events previously labeled as unresolved. As scientists refine their models, the JWST's role in mapping these stress zones will be crucial, potentially revealing a network of interdimensional interactions across the cosmos. The mathematical modeling of these stress points draws on advanced fields like algebraic topology and higher-order tensors, which describe the complex geometries of interuniversal interactions. These models propose that the boundary layer is not a passive interface, but an active region where energy and information are exchanged. The JWST's detection of heteromorphic transformations, where data crossing the boundary changes in nature, suggests that our instruments may only partially capture the information from the alternate universe, with much of it lost in translation due to incompatible physical laws. This limitation challenges scientists to develop new interpretive frameworks, blending abstract mathematics with empirical observations to decode the secrets of the multiverse. The JWST's discovery has ignited a renaissance in human thought, bridging disciplines that once operated in isolation. Philosophers grapple with the implications of a plural cosmos, questioning whether consciousness is unique to our reality or a universal constant that transcends dimensional boundaries. Theologians find resonance in ancient narratives of layered worlds, seeing the multiverse as a modern echo of timeless myths. Meanwhile, neuroscientists explore the possibility that human consciousness may be influenced by interactions with alternate realities, with dreams or intuition serving as faint echoes of other selves. These ideas, while speculative, highlight the discovery's power to unite science and the humanities in a shared quest for meaning. The practical implications are equally transformative. Quantum computing researchers are exploring the concept of multiversal computation, where processors could leverage the differing physical laws of another universe to perform calculations unattainable in our own. Experimental setups are being designed to test for extra universal interference in quantum circuits, potentially revolutionizing computational technology. Meanwhile, space agencies are proposing missions to monitor the interversal boundary, from deep space observatories to propulsion systems that could approach these cosmic interfaces. The dream of touching another universe, once confined to science fiction, is now a tangible goal, driving innovation and ambition in the scientific community. The JWST's discovery has unveiled a startling phenomenon. Faint echoes of the alternate universe are being detected by Earth-based instruments, suggesting that the boundary between realities is far thinner than previously imagined. Observatories worldwide have reported subtle anomalies, phase shifts in pulsar timing, aberrations in neutrino detection, and unexpected noise in deep ice detectors that may be aftershocks from the interversal boundary. These ripples, potentially propagating through higher dimensional space, indicate that the interaction between universes is not confined to the distant cosmos, but may have measurable effects here on Earth. This raises the unsettling possibility that our reality is more porous than we thought, with the potential for subtle influences from other universes to alter the fabric of our own. This fragility of reality prompts cautious exploration. If the interversal boundary allows even trace amounts of foreign physics to leak into our universe, the consequences could be profound. A slight shift in the vacuum state or fundamental constants could destabilize matter, disrupt time flow, or alter the behavior of forces in unpredictable ways. Scientists are now proposing theoretical containment protocols to stabilize these interaction zones, ensuring that further study does not inadvertently trigger cosmic disruptions. The JWST's role as a sentinel at the edge of reality underscores its importance, not just as a tool of discovery, but as a guardian of our universe's stability, guiding humanity through the uncharted waters of a multiversal cosmos. The JWST's revelation has sparked a bold new era of exploration, where the goal is no longer to map the stars within our universe, but to chart the boundaries between realities. The concept of universe surfing, traversing from one cosmos to another, has emerged as a tantalizing, if distant, prospect. Theoretical models are revisiting wormholes, not as shortcuts within our universe, but as potential bridges to other realities. Such feats would require mastery over space-time and energy on an unimaginable scale, yet the JWST's data has transformed this once laughable idea into a serious engineering challenge. Proposals for multiversal observatories, capable of triangulating interdimensional distortions with unprecedented precision, are already circulating among space agencies, signaling a shift from passive observation to active exploration of the multiverse. This dawn of multiversal exploration carries profound implications for humanity's future. If our universe faces existential threats like a big freeze or vacuum collapse, the existence of other realities suggests potential escape routes, pathways to universes where life and consciousness could persist. The JWST has not only expanded our cosmic horizons, but also redefined our narrative, positioning humanity as explorers of a multiversal frontier. As new generations of scientists, artists, and thinkers grapple with these possibilities, the telescope's legacy will endure as a catalyst for a new chapter in human history, where the pursuit of knowledge transcends the boundaries of a single universe and embraces the infinite tapestry of existence. The story of the JWST's discovery is far from over. It has opened a new chapter in the human experience, broadening our understanding of existence and possibility. The telescope has not just peered into the deep past, but looked sideways across a boundary that shouldn't exist, finding a reality that challenges every assumption. As researchers continue to dissect its monumental findings, one thing is certain: the cosmos is far more layered and mysterious than we ever imagined. The JWST has torn through one veil of light, only to reveal another stage where the rules are unknown, the script unwritten, and the possibilities boundless. This is not the end of the story. It is the beginning of a new cosmic saga, one that will redefine humanity's place in the multiverse for generations to come.